So, first of all, ho, ho, ho. This is the last lecture before Christmas, and so I think it's appropriate to dress up in this way, but not for long. So, well, it's too warm already. So we have two questions to solve from the last time, and then we have pleasure again this time, because then Mr. Henschenm will give us an account on the application or the connections between non-distributive algebraic systems and physics, and I'm looking forward to hearing your talk then. So first of all, question 18 asked for the following. We have an equation minus x plus g plus x in a group. So we are in the variety of groups here, and we take this single equation, and one should show that this equation is not solvable, and it cannot be solved in any extension of the group G where we take this element from, provided that G is unequal to 0. Now we can do it in two ways. If we think of the usual form of equations, it would be minus x plus g plus x equal to 0. We know this is a nonsense because equality does not hold. And then we can say, well, g plus x is equal to x, so g must be equal to 0, which is a contradiction. Or we can do it with the criterion we had in mind using the Schwachen-Nullstellensatz, the weak Nullstellensatz, and this is the following. We take this minus x plus g plus x, and if we conjugate this, the polynomial, by adding x in front and subtracting x, this here is a zero-symmetric polynomial. It induces an inner automorphism, and then if you look at this, you see this is equal to g. So g would be in the ideal generated by minus x plus g plus x. And the ideal in the group sense means, of course, in the normal subgroup generated by this polynomial. And so we see we have a non-zero constant in the ideal generated by this polynomial, which makes up the equation. And so it cannot be solved in G, and it cannot be solved in any extension of G. Question 19. Has a similar problem in mind, namely, we had already this equation 2x plus 1. Now we are in the variety of commutative rings with identity, and we have the equation 2x plus 1. And this happens in the ring R, and the ring R should be the integers across integers modulo 2. And we have already shown directly that this equation cannot be solved in R and not in any extension, but now we can again use this criterion which we had in mind, and this criterion asks what's about the ideal generated by 2x plus 1, and if we have these as coefficients, we should better write 2x, that's a equation. That's an variation of 1 times x plus 1 times x. But the identity 1 here is the pair 1, 1. So we should write this perhaps as 2 times x plus 1, 1. And now this 2 here is clearly equal to 0. But if we multiply this by 1, 0 times 1, not 1 times 0, not 0 times 1, what do we get here? We stay in the ideal generated by this polynomial. And if we multiply this, we'll get 0, 0 times x plus, and here we get 0, 1. And so we see, again, we have a constant, a non-zero constant in the ideal generated by 2x plus 1. So this is in the ideal generated by 2x plus 1. And so again, our result, the weak null Stellensatz, tells us that we have no chance to find an extension of R where this equation will have a solution, no matter how big the extension might be. Well, what's this takes care of the questions last time. And now we have the pleasure to hear Mr. Henschenm from Germany. He is not an algebraist from this Vita, but he started in biology and in physics, and so he knows quite a bit more about the possibility to apply non-distributive systems or to regard non-distributive systems in physics. So, Mr. Henschenm, may I ask you to...
Yeah, can you please allow me to share my screen? The moment I cannot share the screen, otherwise it might be difficult to give the talk.
No. I think I've shared the screen.
I will try it again. I can still not share my screen. So the other option would be I send you my slides. If you just open the slides on your computer and share them, then this would also work. So okay, and we'll try it again. No, I still get the message host disabled screen sharing. So maybe the second option would work. So I sent you the slides, you just share them with us, and then I will just tell you to move along when I'm done with. Just an idea. Fortunately, it doesn't work at the moment. So first of all, I'm sorry for this delay.
think I have.
Okay, I will try it again. I always get the message that you're not allowed to share the screen.
Okay, Gunther, you should have on the down end of your screen, there should be a part where it says security.
Yeah.
And there are several options. And I think one of those is participant screen share.
Oh, that's not. That was not. Clicked now. It should work now.
Yes, it does. Okay. Can you see the slides now?
Not yet. Yes.
Yes.
Yes. Now we can.
Oh, from beginning. Yes. Okay. So let's hope. Okay, so now you should just see Near-rings and physics
Yes.
ideas from 1934 till 1992. So
Yes.
first of all, maybe I need to apologize to you as mathematicians. I will distract you from pure math for a few minutes to tell you about ideas to apply non-distributive systems to physics. So I hope this is of interest to you. Otherwise, many apologies for distracting you from pure math. Okay, so there are three persons who mainly developed ideas to apply one-sided distributive algebraic systems to physics. The first was Pascal Jordan, which was a German theoretical physicist who also studied biology, by the way. And he is well known. I don't know whether you know Jordan algebra, which is a variety of non-associative algebras, and he was always interested in generalizing quantum theory. So he was one of the pioneers of quantum mechanics. In 1925, he wrote together with Max Born and Werner Heisenberg the famous paper on quantum mechanics and matrix mechanics. And he had a lifelong interest to generalize the theory he helped to develop. And he's also, together with Dirac and many other people, one of the pioneers of quantum field theory. The other person interested in working with one-sided distributive system was Irving Segal, who was a famous algebraist and mathematical physicist who helped to develop the algebraic formulation of quantum mechanics. If you have heard anything about C star or von Neumann algebras, this was the field of algebra which he helped to develop. And the third and the most recent person trying to apply non-distributive system to physics was Ilya, I don't know how to pronounce it because it's Russian. I hope I do not mispronounce him. Prigogine or Prigogine? Does anybody know how to pronounce him? Unfortunately not. Okay. He was a Belgian, so he was born in Russia and then moved to Belgium, and he got a Nobel Prize for his work on non-equilibrium physical systems. So he was a chemist, a physical chemist by training. And at the end of the 1980s, he tried also to, in a sense, unite quantum mechanics with thermodynamics and formulate a kind of quantum mechanics where the mappings are not reversible, so which is where there's an irreversibility right from the start. And for this, he also developed a formalism where he used what he calls a non-distributive superoperators. I will try to explain what this is later. Okay, so this is the motivation why I wanted to talk about this here with this audience. Okay, so the idea to go beyond quantum mechanics is quite old. It started all in 1934 with a famous paper on a distributive, so two-sided distributive systems called Jordan algebras, which are non-associative but still power associative. So you can see here the Jordan algebra has to satisfy this relation. The bracket denotes the associator, which measures how far you're away from being associative. And the Jordan algebra needs to satisfy these two relations. So the first one is called the Jordan identity, and the other one is called flexibility. Flexibility condition is only important if your algebra is non-commutative, because in a commutative algebra it's trivially fulfilled. So many people, if you look up Jordan algebras, they only look at the Jordan identity because they work with commutative Jordan algebra. So the initial hope by Jordan, Wigner, and von Neumann was that maybe we can use Jordan algebras to move beyond quantum mechanics. And obviously this didn't work. Otherwise, I would stop talking now, because then we would have a generalization of quantum mechanics, which is two-sided distributive, and then we would not be interested in working with near fields or near rings. The trouble with Jordan algebras is that most Jordan algebras can be derived from associative algebras by defining a new product for the elements of an associative algebra. This is the so-called Jordan product. It was first discovered by having a closer look at the observables in quantum mechanics. So in quantum mechanics, the things you can measure are represented by Hermitian matrices or operators. And if you use the ordinary matrix or linear operator product, they do not close under this product. So the product of two Hermitian operators is not a Hermitian operator unless the operators commute, which is in the context of quantum mechanics trivial, because quantum mechanics from an algebraic point of view differs from classical mechanics by the fact that the observables do not commute. So you only have this product only closes under trivial situations, and that's why Jordan developed his Jordan product. You take the ordinary matrix or operator product, so AB plus BA, and you form the anti-commutator, so AB plus BA, and then use the prefactor of 1/2, and this then gives you a Jordan algebra. And Jordan's hope was that there are many examples of Jordan algebras which are not coming from associative algebras. Unfortunately for him, it turned out that this doesn't work. There's only one so-called exceptional Jordan algebra, which is the algebra of 3 times 3 Hermitian matrices over the octonion. So the octonions or the octonian algebra is an intrinsically non-associative algebra, which is also non-commutative Jordan algebra. But the algebra of 3 times 3 Hermitian matrices over the octonions is just way too small to serve as an algebraic generalization of quantum mechanics. And that's why Jordan continued to look for generalizations. And already in 1934, John von Neumann told him, so Jordan wrote a long paper about the axiomatics of quantum theory already in 1934. And he thought he could derive the distributive laws, both distributive laws, from his axiom, so that one could say that distributivity is required for quantum theory. But John von Neumann spotted some weak points in his in Jordan's derivation of the distributivity of the Jordan product and the multiplication of quantum mechanical operators. So one was the condition that minus A times B is equals minus AB. And the other was that if you take that A in brackets times in brackets 2B equals 2 times in brackets AB. So these were two conditions which Jordan thought would be physically necessary, and von Neumann told him you have used them implicitly in your derivation of the distributive law, but you didn't give any concrete reasons why any kind of physical system needs to satisfy these relations. And this was in 1934 the first hint. So it was actually coming from John von Neumann, who is in some quarters, some people think he was quite conservative when it comes to the formalism of quantum mechanics, but this is not true. John von Neumann was one of the first persons to point out that one might have to use a nonlinear version of quantum mechanics. So this is somehow different to what many people think about him. Okay, so this was just the introduction. So Jordan tried to find a generalization of quantum mechanics. He first tried it with power associative and non-associative algebras. This didn't work, and then John von Neumann informed him that he might have to look at one-sided distributive systems. So this is the paper By the way, if you're interested in these things at all, I could send around these papers to the members of this lecture. So most of them are unfortunately in German. So if you cannot read German, it will not help. But for the people who can read German, it might be of interest to follow this line of thought, which started in 1934. So he submitted it already in 1933, but it was published in 1934. And it's called, well, translated it means about a multiplication of quantum mechanical observables. So this was the first, I think it's the first mentioning of a nonlinear system in quantum mechanics. Okay. So then the next person who looked at one-sided distributive systems was Karl Scheuer in Germany. I think in the community of near-ringers, he is famous for discovering topological near fields over the real numbers. And what I will show you later is that Karl Scheuer was inspired by Jordan's work on non-associative generalizations of quantum mechanics to look for near fields. I will show you later what he's written about this. So he looked for topological near fields over the real numbers, and he found, well, that the fields of real and complex numbers from, in a sense, trivial near fields because they are commutative and distributive, but nevertheless, it's a near field in a very general sense. So to real and the complex numbers are example of near fields over the real numbers, which are well known and from the perspective of near-ringers, maybe a little bit trivial. The other thing he found was that the skew field of quaternions is also one of the near fields over the fields of real numbers. But then he also found proper near fields, which are obtained by deforming the multiplication in the skew field of quaternions by using the Dixon process. I think Mr. Pilz talked earlier about this in one of his earlier lectures. And he defined for two quaternions this multiplication shown here. So you have a kind of you have a coupling of function which deforms the multiplication in the quaternions, and this is this function here. What's interesting is that this proper near fields, so which are one-sided distributive, do not have the real numbers in the center. So the real numbers do not commute with every, I call them Karl Scheuer numbers. I think in the literature they are just called twisted quaternions because you twisted the multiplication of the quaternions. And this might be later of interest because normally you consider real numbers or real functions to describe classical systems in physics. This would mean that yeah, you might have trouble defining a classical limit if you try to develop a generalization of quantum theory using the Karl Scheuer near field. Okay, so this is his paper from 1940, where he writes about determining all continuous near fields over the field of real numbers. And he quotes two motivations. One is axiomatic. So are there any systems with only one-sided distributive multiplication where the multiplication is continuous over the real numbers? And the second one, here that in German, I translated it into English. The second reason is of physical nature. In 1933, Jordan published a paper on possibilities of generalizing the quantum mechanical formalism. In this paper, he dropped the axiom of this, he dropped the associative law of multiplication. And then Karl Scheuer says it's also of interest to learn whether there are any generalized physical system where only one, where the right distributive law is not valid, where only one distributive law is valid. And because in physics you only work with continuous systems, we need to look for topological near fields. So one of the earliest papers on topological near fields quotes the idea to generalize quantum mechanics by using near fields as its motivation. I think it's not so well known either for physicists nor for mathematicians. Okay, and then again 7 years later, Irving Fiegel developed a general formalism for quantum theory, And it's a kind of infinite dimensional generalization of Jordan algebras, because the early papers on Jordan algebras only dealt with finite dimensional systems. And what he's required, he had quite a few axioms. The one axiom he used was power associativity, like Jordan earlier, but what he did not require was two-sided distributivity. So he showed that it is possible to formulate a generalized quantum theory, even for infinite dimensional systems, without requiring the distributive law. He could not find any examples of satisfying his axioms, but at least he could show that it is reasonable to some extent to formulate an extension of quantum theory where you drop the distributive axiom. Okay, and then between 1915 and 1952, Jordan and von Neumann continued not a collaboration, but they exchanged email letters, not emails, normal letters, of course, we were in the 50s, sorry. So, and Jordan wrote 3 papers where he described the application of one-sided distributive systems in physics. And he even went so far, he was interested in near fields, but he was also interested in, he was always interested in non-associative systems. So this was his pet mathematical theory, everything related to non-associativity. And he was also interested in non-associative near fields, quasi-fields, and in near-rings, also non-associative near-rings. And he also worked with near-rings with non-commutative addition. So until 1951, Jordan considered commutativity of addition to be a basic axiom for meaningful physical theory. And he was one of the first to work with what's now called polynomial near-rings and distributively generated near-rings. Why was he interested in working with one-sided distributive systems? His motivation was that he thought we need a generalization of quantum theory because we have infinities showing up in quantum field theory. Because in quantum field theory, you can work with arbitrary short distances and arbitrary high momenta and energies, and this leads to infinities in the calculations of integrals and, well, basically physical processes. And Jordan thought we need to generalize quantum theory because in quantum theory, we cannot measure with arbitrary precision pairs of observables. I think you might have heard about the uncertainty relation of Heisenberg, which tells that you cannot simultaneously measure position and momentum of a particle with arbitrary precision. But what, at least from a formal point of view, is still possible in quantum theory is to measure, let's say, the position with arbitrary precision. Then you have an infinite imprecision for momentum. But at least in principle, you can still measure with arbitrary precision the one observable. And Jordan thought that we might need to generalize the concept of space and introduce a minimal length, which can be resolved by measurement, and where not only pairs of observables cannot be measured with arbitrary precision, but a single observable cannot be measured with arbitrary precision. And he had 2 main ideas how to make this work. One was to work with one-sided distributive system, and later in the 1960s, he worked with non-power associative algebra. Okay, so in 1956 and 1957, 2 American mathematicians could develop systems which satisfy the axioms of Siegel, which I introduced earlier, and which were one-sided distributive. But for some reason, this never caught the interest of mathematicians or physicists. And it was proved in 1992 that these systems cannot work as a generalization of quantum theory because they're running into conflict with special relativity. So if you would use the Sherman or Lorenz-Lager systems to model a physical system, you would be able to signal faster than the speed of light, and this would break special relativity. This is one of the great caveats if you try to generalize quantum theory. So if you try to move beyond the complex Hilbert space formalism, you almost immediately run into conflict with special relativity. the main point is that you have some non-local correlations in quantum theory. I think you might have heard about entanglement or EPR correlations. And in quantum theory, the linearity of the theory prevents you from using the non-local correlations to signal faster than the speed of light. And this is one of the biggest showstopper if you try to generalize quantum theory. If you try to describe two subsystems of a larger system, in quantum theory, you use the tensor product. And if you stick to this formulation, you're almost immediately forced to use linear operators on a complex Hilbert space, because even if you try to work with a quaternionic Hilbert space with normal quaternionic multiplication, you do not have a unique tensor product because the quaternions do not commute. And this already brings you into trouble with having independent subsystems and might also give you the possibility to signal faster than light. So if you take this as a starting point, you're almost immediately forced to use a complex Hilbert space with linear operators. And as far as I know, so it's very difficult to move beyond this. Otherwise, you would really have to change the entire formalism of quantum theory. But this was not known in the early 1950s. So Jordan was still interested in generalizing quantum theory, and he used the work of Karlsruhe as a kind of inspiration to develop his own one-sided distributive system. And I told you Jordan was always interested in non-associative systems, so he took the ring of matrices and deformed the multiplication in the ring of matrices by using the matrix exponential function. And if you use the matrix exponential function to deform the matrix multiplication, you do not only destroy linearity and distributivity, but also the associativity, because the matrix exponential function is it does not satisfy the product rule, which I think Mr. Pilz also introduced when we were talking about the Dixon process in near fields. You have to satisfy a certain relation if you deform the multiplication to make sure that your multiplication remains associative. And if you do it like Jordan did it in the 1950s, you lose the distributive law, but also the associative law. What you would also try to do is use this product and then use the Jordan product to get a commutative but non-associative and one-sided distributive, well, near algebra. And he stopped because this here doesn't work. So Jordan always required, oh, sorry. Jordan always required that the operation of multiplication can be derived from forming, from addition, so from forming sums, and from squaring of elements. And he could not find an example of a one-sided distributive system where you can derive the multiplication in the system from the operation of squaring an element. And that's why he stopped to work on this one-sided distributive systems in the 1950s. What's interesting about this example here is that if you use the Jordan product and this deformation of the ordinary matrix product, you get a non-associative near ring which is formally real. Formally real means that if you have a sum of squares, the sum of squares is only 0 if every squared element in the sum is 0. So you don't have nilpotent elements in your algebra. And I found this quite interesting because normally people say if you lose the distributive law and the associative law, you lose a lot of structure. But at least Jordan was able to find a one-sided and non-associative nearing, which is at least formally real. Okay, one thing I would like to tell you is that Jordan also discussed what is algebraically required to have measurements in quantum theory. So if you think about a measurement, let's say you have a measurement device and it has a scale and it has a pointer which shows you the value of an observable. And Jordan looked what is required so that this procedure works, and he said you need a power associative algebra and something which I think we would call it monodistributivity. So you require that every single element in your algebra of observables generates a normal algebra. So the GAlgebra formed by every single element of the larger observable algebra is commutative, associative, and distributive. And Jordan said that this is required to have measurements in the usual sense. So if you work, for example, with a non-power associative algebra, you cannot have a physicists call this pointer state. So if you would have a measurement device, the pointer would always move between left and right, and you would never have a certain and definitive value of your measurement if you don't have monoassociativity or power associativity. And he said the same is true for a monodistributivity. So for example, if you had a near ring where one element forms a non-trivial sub-near ring, so then this would not be a suitable tool to develop a physical theory. By the way, I don't know whether there are any near fields or near rings where a single element forms a non-trivial near field or near ring as a substructure. So maybe this is just purely academic, and near rings are so tame that this problem never shows up. It's different in an non-associative algebra because there are examples of non-power associative algebras, but maybe near rings are more tame with this. I don't know. Okay, so this was his work on non-associative near rings, and he also briefly looked at associative near rings, but with non-commutative addition. He looked at the functions on a non-abelian group, and he defined multiplication as function composition, and addition as the ordinary multiplication of group elements. And then he formed polynomials from the group elements and formed a polynomial near ring. And what's important, the generators of his near rings are the endomorphisms of a non-abelian group, and endomorphisms are distributive. So he used distributive elements to generate a near ring. And he proposed to use this distributively generated near rings as a possible generalization of quantum theory. What's important here, commutativity of addition was one of the basic axioms which Jordan could also derive from the formalism of quantum theory. So here Jordan really moved beyond quantum theory because commutativity and associativity of addition and power associativity of multiplication belongs to the main basic axioms of quantum theory. And in this case, you could not add two observables and get another observable. So the sums of observables would not be additive. And you would have to develop a totally different measurement theory than the measurement theory which is used in quantum theory. Okay. So then we move forward to 1966. So then for 14 years, nobody looked at non-distributive system in physics. But then Harold Brown at Michigan University wrote his PhD thesis under the supervision of Hans Zassenhaus, by the way, on near algebras, which are the one-sided distributive generalization of algebras. And he could show that all differentiable near algebras reduce to normal algebra. So I could send around the PhD thesis. So maybe the mathematicians can have a closer look at Brown's definition of what's differential, because nonlinear operators do form a near algebra, and this would mean that you cannot have any kind of functional analysis with nonlinear operators. And I think that's too restricted or too harsh a statement. So I'm not quite sure whether I really got what Brown wanted to say in 1966. But he also quoted Jordan's idea to use near algebras to generalize quantum theory. And he also discussed the Karcher near fields because they have continuous multiplication. Okay. Then in 1974, the German mathematician Johannes André tried to generalize vector spaces by developing near vector spaces. And he also quoted Karcher and Jordan as a motivation to develop the theory of near vector spaces as a kind of nonlinear algebra. And he proposed to develop a generalized Hilbert space over the Karcher near field. His near vector spaces are formed by an abelian additive group, which then form the elements of the commutative group under addition from the vectors, and then he takes endomorphisms of this abelian group as the scalars, which form the semi-group, and he then drops the distributive axiom of vector spaces to develop a near vector space. He could prove that all near vector spaces are direct products of what he called regular near vector spaces. What's of interest here, if you try to generalize quantum theory, is that the structure here is closer to classical mechanics than to quantum theory, because you do not have tensor products for near vector spaces. And I think, if I got it correctly from Professor Pilz, I asked him, there's no definition of tensor product for near rings and near fields in general. So you would have a very different way to compose subsystems or physical systems which are made of, well, other systems than in quantum mechanics, because you cannot use the tensor product. Okay, so I will just briefly describe what Andre proposed with the Karlsruhe near field. So this once again is the multiplication in the Karlsruhe near field. So A and B are two quaternions. Well, I is the complex unit, so I squared is -1, and T is a real number parameter which can vary, and if you vary T, you get a different near field. So the near fields are not isomorphic if you change the T here in the multiplication. And he proposed to define a generalized Hilbert space, which is shown below here, over the Karlsruhe near field, so with elements from a Karlsruhe near field, and with an absolute value of the with the squared elements, with squared absolute values of elements of the Karlsruhe near field as a generalization of the Hilbert space. And his hope was that one can generalize quantum theory by using this generalized Hilbert space, which would be a kind of nonlinear Hilbert space, if you like it like this. Would like to describe it like this. I quote his motivation. So maybe this near vector space allowed to get new insights into functional analysis and quantum theory and possible generalizations of quantum theory. So this was his motivation. Yeah, and then we are coming closer. Then for 14 years, nothing new happens. And then in 1988, Prigogine tried to find a stochastic and nonlinear generalization of the Schrödinger equation, because he wanted to solve the measurement problem in quantum theory. So in quantum theory, you have a superposition of different physical states, and everything is, yeah, in a sense, uncertain until you measure something. Then all of a sudden you have a sharp value, and you have only one value and not a superposition of different values. And the normal formalism of quantum theory, it's really hard to get this. So you have to add a different axiom. It's called the projection postulate into quantum theory to get this. And Prigogine and Petrovsky in the United States were interested in developing a generalized quantum theory where you can describe the transition from quantum to classical without having this additional axiom. And they work with operators which act on other operators. So such operators are called super operators, and they did not work in a Hilbert space, but in another space, which is described here. And the interesting thing about a super operator is that it's non-distributive with respect to multiplication. So if a super operator acts on the product of two operators, it's not the same if you just let the super operator first act on one operator and then form the product with this. So in this sense, this is non-distributive. And he also concluded that in this case, you have the uncertainty for single observable, regardless of other observables. And this is like Jordan envisioned in 1952. The second thing is, which I would like to say, is a general remark about nonlinear systems. Nonlinear systems can be modeled by near rings, and the composition of mappings is equal to matrix multiplication in finite dimensional linear systems. So, and finite dimensional linear dynamical systems form rings, and also infinite dimensional, sorry. But what's interesting is nonlinear dynamical systems form near-rings, and I took that from the book by Professor Pilz and Liedl, Applied Abstract Algebra. And in this case, matrix multiplication becomes composition of mappings. And the set of nonlinear operators does form a near-ring, even in near algebra. So if you're interested in a nonlinear generalization of quantum theory with nonlinear dynamics, you may need to work with near-rings and near algebras. And there are some ideas in this direction which are called spontaneous localization theories, where they modify the dynamics of quantum mechanics by adding a nonlinear term to the Schrödinger equation. And in this case, you would probably have to deal with nonlinear dynamical systems and might need to work with near-rings. And even though there are some people trying to generalize quantum theory by making it nonlinear, they never mention that they are working with the near-ring. And the near-ring community, apart from Andre, so far does not look into quantum theory. So there seems to be a quite kind of divide. Okay. One thing which I would like to see is whether there are any link between well, near-rings and super operators. And I asked one of Pierogi's co-operators, Gonzalo Ordonez in America, and he told me that the super operator sum is also non-distributive with respect to the super operator multiplication. This is shown here. Oh. So the super operators also do form a near-ring. So this would then be an example of a near-ring which really was used in a kind of physical application. Okay, so if I did not bore you too much with this lecture, there's a preprint which I prepared with an Austrian researcher named Liebmann and with Horst Rüegg, who was a PhD student of Jordan in 1968, which you can find on the archive.org, and where we discuss the idea to move beyond quantum theory starting from 1932 until 1972. We also discussed non-power associative system because Rüegg wrote his PhD thesis about such algebras. Okay. Yeah, the references. As I told you, if you're interested, I could send some of the reference to the people who are interested in this topic. And that's it. So I hope I did not distract you too much, and yeah, you found it somehow interesting or useful, and then now you can continue with your lecture.
Well, thank you very much, Mr. Henschenm. I wish I knew about as much in physics as you know in algebra. So the main, if you think of algebraic systems in quantum mechanics, the elements of the algebraic systems would usually be observables or operators.
Yeah.
And the question is to get a good way of computation in this algebras, which fit to the reality in physics.
Yes, that's it. So this is still an open question. So frankly speaking, at the moment, there is no experimental need to move beyond the quantum mechanical formalism. So it was only speculations by people who were unhappy with the way quantum mechanics was formulated. And the original motivations in the 1950s to get rid of the infinities was, let's say, somewhat solved by the renormalization program. So if you read the works of Feynman and I forgot his name, he was also an American in the 1970s. They work with, it's called the renormalization semi-group, so where you just say that the infinities are somehow swept under the carpet by using measured quantities, and then you put the divergent integrals or quantities into the measured quantities like electric charge or the mass of the electron, and then you can continue with your calculations without having to deal with the infinities. This worked quite well for all quantum theories apart from gravity. So it doesn't work in quantum gravity. That's one of the main reasons why we do not have a quantum theory of gravity, because the renormalization program doesn't seem to work for quantum gravity. And there are even some people who try to develop quantum gravity who use generalized algebraic systems. There's one it's called group field theory, and they, for example, work with systems where addition is non-commutative as well. So in quantum mechanics, only multiplication is non-commutative. So they're coming closer to near-rings because at least they don't require addition to be commutative. But I think they still work with distributive systems. So, but as I said, they're coming closer to a near-rings formulation of physics. So, yeah.
Yeah, thank you. To the other participants, do you have some questions to Mr. Henschenmacher? Okay, but you have the email address. I sent it out, and so you can get into contact with him very much. So
If
thanks
anybody
again.
interested in getting papers. So.
Yes. So if you can send out the papers, as you mentioned before, that really would be very good, that we can have a look at this in a longer for a longer time, and to think about these connections.
Okay, so well, then thank you very much that I could talk so long about this, and so I hope then yeah, it was helpful, and then I won't distract you any further.
Thank you very much, and also thank you very much to Jakob for giving me the hint. Otherwise, it would have it would have not worked, and so you saved the talk.
Yeah, thank you very much, Jacob. I'm very glad as well.
Yeah, I'm faced with this problem every week in my exercise class. The students ask me, I cannot share the screen. So I know where to find that.
Okay, good. So let's continue with our regular course. And we stopped last time at equations which is model in some way the thing that two non-parallel lines should have a unique point of intersection. And we had the idea that to look at equations of the type xa is equal to xb plus c. All these equations should have a unique solution unless xa is always the same as xb. Then of course it depends on c if you have solutions or not. So we can take a
ഞാൻ എന്തെങ്കിലും പോസ്റ്റൽ നമ്മൾ എന്റെ വിദ്യാലയത്തിൽ ഇപ്പം കുറേ ആയി കാണാനായിട്ട് ഞാൻ വിചാരിച്ചത് ഇതാണ് പ്രേമമാഷ്
that A and B are congruent if and only for x in n we have xa is equal to xb. So if we have this thing here, then we can say all equations of this type where A is not congruent to B have a unique solution. And if this is the case, we usually call n a planar near-ring. And usually one also adds another thing, one to avoid that we have a trivial situation, and so we also require that the n factored by this relation has at least 3 elements. So there are at least 3 congruence classes. Otherwise, things would become very, very trivial. maybe I should mention the big names in this area who have worked there. One is Jim Clay, who started with this, and then another an Italian mathematician, Giovanni Ferrero. Also worked in this theory. Then one you know very well now, Mr. Batch, also joined them in some work, and more recently, Wen Funke from Tainan also worked on this class of planar near-rings extensively. One thing one can say very quickly before we go to examples is that if you have a planar near-ring, then the planar near-ring is automatically zero-symmetric. This was shown by Jim Clay. Let's call it a claim here. If n is planar, then n is zero-symmetric. We might also indicate this in that way. And why is this true? That Clay has developed a technique for proving things about planar near-rings in the following way. Take some n in n, and n should be not congruent to 0. Then you can say, if we look at the equation, xa take n from n and take, excuse me, an element a which is not congruent to 0. Then we look at the equation xa is equal to x times 0 plus 0, I think. Yeah. Now, since a is not congruent to 0, this equation should have a unique point, a unique solution. But we find two solutions, namely if we take if we take n here, and also n times 0, what did I do? Excuse me. No, excuse me. 0, excuse me. 0 is a solution of this, and n times 0 is also a solution, because n times 0 times a would be 0, and you have is equal to n times 0 plus 0, and so we get two solutions. They would be different if n times naught is not equal to naught, and so since we have only one solution, n sub naught must be equal to, no, excuse me for the point here. So if we have a planar near-rings, we automatically have a zero symmetric case. And now let's look at some examples. The first example was given by Jim Clay already right in the beginning, and that's the following. Let V be a normed vector space. So it's equipped with a norm. And let's take the addition as it is in V, and let's take a multiplication V times W is defined as the norm of W times V. So it's a multiple of V. And this was one of the starting points of Jim Clay to see that this is a nearing. And in fact, if you replace V by V1 plus V2, you have V1 plus V2 here, and you can, since this is a scalar, you can multiply this. And so you get one-sided distributivity, but not two-sided distributivity. And in order to find that this is a planar nearing, we first better look what means that two elements are congruent. So we would be, say, congruent, let's take W1 congruent to W2. That happens if for all V, we would have V times W1 is equal to V times W2. And now by the definition here, this means that the norm of W1 times V is also the norm of W2 times V for all V. And so this is equivalent to saying that W1 and W2 have the same norm. And so we see the equivalence classes. If we take, for instance, the vector space R2, the two-dimensional one, what does it mean for two elements to be congruent? It means they have the same norm, and so all elements with the same norm, they are just on a circle around the origin of radius, this norm here. And so we see a good way to imagine how equivalent or congruent elements look like. And now we can easily say what happens if we have an equation x times A equal to x times B plus C. If A and B are not congruent, that means that the norm of A is not the same as the norm of B. Well, in this case, we can simply take the definition of the multiplication here, and what we have is that it amounts to that the norm of A times x is equal to norm of B times x plus C. And so since these are scalars, it's very easy to find the unique solution. The unique solution, of course, is just C divided by the norm of A minus the norm of B. And so you see that these equations have a unique solution always if A and B are not congruent. And so this is a nice way to get a planar nearing. Of course, you get infinite planar nearings in this way. And in order to get finite nearings, we can simply get
How to define a field? Yes.
Number 2 here, because it can be shown that if you have a finite near field, then unless it has just 2 elements, so if the number of elements is at least 3, then N is automatically planar. So all finite near fields are planar near fields, and then there was a search if if in the infinite case, if you can find non-planar nearings, and yes, there's a paper that one can find infinite near fields which are not planar of every characteristic. Most important for us, however, is example number 3. Machinery to get a number of planar nearings in the following way. Start with a finite field. So N would be the color field of order P to the N. Take the usual addition of this field, and then you define a new multiplication in the following way. P to the N minus 1. That's the order of the multiplicative group then. P to the N minus 1. If you have the way to divide it into 2 parts, like S times T, where S and T are bigger than 1. So if you have a factorization, a non-trivial factorization of this, then you can find a multiplication the following way. First of all, I mentioned this is the size of the multiplicative group. And you know that the multiplicative group of a finite field is cyclic, so it has a generator, and every cyclic group of order P to the N minus 1 has for every divisor, like S here, as a cyclic subgroup of this order. So let S be a cyclic subgroup of order small s, and it can be said it is unique. S be the subgroup of the multiplicative group. Let's write it as GF of P to the N star of order equal to small s. And we'll do this in an example right now, or right after that. That means that we can say that the multiplicative group of this field, this decomposes into cosets one coset is S itself, union with V, say 1 times S, union, and so on, up to say V. Well, let's write it as say V2, and the last one would be Vt. That's this cofactor here times S, and V1 should be equal to 1 to make things a little easier. Now, if you have an element B in here, B will be in one of those, and this, you know that the cosets are direct split up of these cosets. There's no point of intersection, so B belongs to exactly one of these cosets. So if B is in, say, Vi times S, then you find this way to write B as Vi times some small s, depending on B. So that's S sub B. And now you define finally the multiplication in the following way, that you write A times, depending on S, B. This is defined, it should be 0 if B is equal to 0. And if B is not equal to 0, it should be A times S sub B, like in here. And now it's fairly easy to find out that this is a planar near-ring, and this should be done in question 20. Show that this example in number 3 yields planar near-rings. And also to find out what A congruent B means in this case, and we'll see it in the example right now, that it's very easy to find that. So starting with this finite fields, you can find planar near-rings, and we might do it in the following way. An example of this example, so it's example squared, so to speak, would be that P to the n is equal to 7. So n is equal to 1. It's even a finite prime field. And the order of the multiplicative group is 6. So we decompose 6 into 2 times 3. That's the only way to do it non-trivially. 6 would be as 2 times 3. Did we have the S and T? We want S3, 3 times 2. So this would be our S and this would be our T. And now we have to look for a subgroup of the multiplicative group of order 3. And that's very easy to do because we have a finite prime field. So our subgroup S would be the only one which could be 1, 2, and 4. That has order 3. And the only coset would be then to take one element which is not in here. Of course, we might take 3. So 3 S would be 3, 6, and 3 times is 12. 4 is 12, so it's 5. And so the multiplicative group of this field of order 7 decomposes into 2 subsets in a disjoint way. And these 2 subsets are S and 3S. And now what's the next command here? We have this, and if we have to define the multiplication now in order to do it. And so if you have A and B, the multiplication corresponding to the S equal to 3 times B would be the following. Disregard this first case when B is equal to 0 for the moment, so that we don't have to distinguish these cases all the time. And what about the SB? Well, it's just A times S sub B. So it would be a good idea to find what S sub B means. So if we have B, 1, 2, 3, 4, 5, and 6. We have to find out 1 belongs to S. So S sub B, here we go. So if B is equal to 1, it's in the first coset, the subgroup itself. So B is equal to B in this case. So for elements in S, we get S sub B 1, 2, and 4. They remain unchanged. And what happens in the other cases, like 3? 3 is now 3 times in 3 times S. So 3 would be 3 times 1, of course. And so S sub 3 would be 1. S sub 5, S sub 5 would be 4. And here we would get 2. You can do it easily. So from that, we have now a good way to find out what S sub B is. And then we know the multiplication already, and we can perhaps start with this multiplication to make it into a table. And I want to omit all the zeros on the first line and first column, because they all will give a product equal to 0, because we have shown that the nearing must be zero symmetric. So we only have to take care of 1, 2, 3, 4, 5, 6. And we'll need this table again later on. So what can we say in the first row? 1 times let's write it down again. A times 3B is equal to A usual product with S sub B. So if we take 1 here for A, then we get product A times S sub B, but we have done all the S sub B's already, and we get here 1, 2, 1, 4, 4, 2. If if B is equal to 2, then S sub B is also equal to 2, and so we get just twice as much as we had up here. We get 2, 4, 2. 2 times 4 is 8, which is 1, 1, and 4. And the same with 4, because it's also in the subgroup S. So we take 4 times the first row. It's 4. 4 times is 1. 4. 4 times 4 is 16, which is congruent to 2 modulo 7, 2, and 1. And for the others, 3, 5, and 6, which are in the second coset, we have to multiply 3 with the S sub B's here. And the S sub B's are written down here. So we have 1 times 3 is 3, 3 times 2 is 6, 3 times 4 is 12, which is 5, 5, and 3 times 2 is 6. And 5, similar, it's again the same to multiply with 4, like in 4, so we get the same here. No, it's 5 times the S sub B's, so it's 5. 5 times 2 is 10, which is 3. 5 times 4 is 20, which is 6. 6 10 is 3. And finally, for 6, and I'll do it intentionally to that we get practice, and we can see quite a lot from this thing here as well. 6, so we have to take 6 times these. It's 6. 6 times 2 is 12, which is 5. 6. 6 times 24 is 3. 3 times 6 times 2 is 5. And now we can already see a lot from this picture here. We can see that all rows here have either the elements 1 to 4, or they have the 3, 5, 6 here. And there are the same number of rows with the property that the elements come from the first coset and from the second coset. And each element here appears exactly twice. So there's a lot of symmetry and a lot of regularity in this multiplication table. And we'll find that we get even more similarities there. Again, it would be good to check what A congruent to B means. That happens if and only if for all x, or let's write for all n, n cross A is n times B. I omit the 3 here now for the multiplication sign. So this we get for all n, n times S sub A must be n times S sub B. And this happens for all n. We have this is the usual multiplication in the field. And so we get that this happens if and only if S sub A is equal to S sub B. Which means that we can say which elements are congruent and which are not. So you see the congruences here already which elements have the same S sub something. We see 1 and 3. So 1 is congruent to 3. 2 is congruent to 6. And 4 is congruent to 5. So these congruent elements, they are also usually called equivalent multipliers. And from that you see that for instance, 2 congruent to 6, but are the set of all n times these elements of A. Well, that's just the corresponding column. So the corresponding column of congruent elements must be the same. So the column for 1 and for 3, you see down here, they have the same columns. 2 and 6 have the same columns, and 4 and 5 have the same columns, which means that we could have done easier getting this multiplication table if we have known, if we would have known that before. But on the other hand, it was quite good to look at this. Yeah, and what about the thing with planarity equation? Oh, no space now. Let's take x times a equal to x times b plus c, where a and b are not congruent. Then this means that x s sub a is equal to x times s sub b plus c. And from that, I don't, since s sub a and s sub b are not the same, because they are not congruent, you can easily see what the solution is. Like before, we can divide c by the difference sa minus sb to get the unique solution here. That means that we have now a nice example, a very concrete example of a planar looking this way. And from that, we can find a lot, as I said, a lot of symmetries in here. Maybe if you, to close it up now, maybe if you look at this, do we have an identity here? And we can see no line fulfills this. We do have one-sided identities here. In fact, 1 and 3 would be of this type, but we have no two-sided identity. And next year, we will find that this is typical. We'll find that three things are equivalent. The first thing is that the planar nearing contains an identity. That happens if and only if the planar nearing is a near field. And this happens if and only if the congruence just reduces to the identity. And so it's very typical that a planar nearing has no identity. And so if one wants to look at examples of nearings without identity, planar nearings are a very good way or area to look at. So time is over, and I would like to thank Mr. Henschenm again for doing part of the talk, and I would like to wish all of you a happy Christmas season, provided you celebrate it. And I wish you a very, very good New Year, Western New Year 2021. And I hope it will be better than 2020. Let's be happy when this crazy year is finally over. Yeah. So all the best. Stay healthy, and I hope to see you again on the 11th of January. That's the next lecture, and then I will show you how to use these Planar in order to apply directly to parts of your life. For instance, when you suffer from some uh, yeah, unknown medical problems, or if you want to improve the yield of your fields where you buy where you grow crops and so on. So these pioneerings, they have very, very concrete applications, and I'll also show you how to do the statistics in order to find out what you want to achieve. So thank you very much.
Thank you very much.
Have a good time.
Happy Christmas and Happy New Year.
Merry Christmas.
To everybody. Good holiday season. And thank you very much for giving me the opportunity to give this lecture.
It was a pleasure.
Very nice.
I think for all. So bye-bye.
Bye.